The Webb glance is such a long way out that it's catching light that has been voyaging for over 13 billion years yet. The universe has been extending, and thus the light has been extending for the most distant worlds. We're thinking back in time nearly to the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we allude to as the singularity. As of now, this is how we might interpret the Big Bang hypothesis. Anyway, the James Webb Space Telescope, JWST, has revealed significant mysteries about the birth and development of the universe, leaving us dumbfounded. Prestigious physicist Brian Cox has proclaimed that the noteworthy discoveries made by the JWST might actually reshape our understanding of the universe as a whole. Join us as we dive into these new heavenly discoveries that promise to change our comprehension. The James Webb Space Telescope, named after the recognized NASA executive James E. Webb, remains as a wonder in current galactic investigation. This telescope represents a huge mechanical leap forward from its ancestor, the Hubble Space Telescope, coming about because of a cooperative effort between NASA, the European Space Agency, and the Canadian Space Agency. The JWST surpasses the abilities of its herald. It utilizes cutting-edge technology and a design enhanced for concentrating on the universe in remarkable detail. Not at all like the Hubble, the JWST conveys clear and sharp pictures of far-off heavenly bodies working primarily in the infrared range. This interesting component permits it to infiltrate astronomical residue and catch divine items that were beforehand stowed away from our view. With its monster 6.5 met primary mirror, made out of 18 hexagonal sections, the JWST diminishes the Hubble's reflector size, situated roughly 1.5 million km away from Earth at the second range point L2. It circles the Sun in a state of harmony with Earth, ensuring a steady and continuous view of the universe. While looking into the far-off corners of the universe, it involves exploring light years, but it also involves a type of time travel. The JWST uses infrared instruments to notice heavenly objects and events going back billions of years. The light emitted by these objects, because of the expanding universe, goes through redshift, moving from the apparent range to the infrared frequency or longer. Luckily, the JWST can identify infrared light radiated by heavenly bodies at extreme distances, empowering researchers to study the introduction of stars, investigate galaxy development, and examine exoplanet atmospheres. Its latest historic discovery involves identifying an incomprehensible mass of cosmic systems at the edge of the discernible universe. This finding challenges the validity of the theory of how things came to be, provoking a reassessment of our key cosmological assumptions. To better understand how we arrived at this point, we should take a short excursion through the history of space investigation. Early civilizations like the Greeks and Chinese laid the foundation for understanding planetary movement by noticing divine bodies. Newton's regulations in the 17th century gave a hypothetical structure for space travel. In the mid-20th century, Edwin Hubble, an influential astronomer, made historic revelations in cosmology and observational space science. His uncovered that far-off nebula were isolated worlds long past the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law, established by him, showed that galaxies farther away were moving away at higher rates, giving proof to the expansion of the universe. The post-World War II history of space exploration marked the beginning of the space race, with the Soviet Union Sputnik in 1957 as the first artificial satellite in orbit, Yuri Gagarin's orbital trip in 1961, and the Apollo 11 moon landing in 1969 were crucial accomplishments. Fast forward to 1990 when the Hubble Space Telescope was launched, giving exceptional clarity and stunning insights into the universe. The journey from ancient observations to the technological wonders of the James Webb Space Telescope showcases the constant development of how we might interpret the universe. It uncovered the boundlessness of space and changed fundamental thoughts in astronomy. Take the Hubble Space Telescope HST for instance. It snapped the famous pillars of creation image in the Eagle Nebula, revealing a star nursery formed by massive columns of gas and dust. Another significant accomplishment was the Hubble Deep Field, capturing a huge number of galaxies in a seemingly void patch of space. The HST also dove into exoplanet atmospheres, pinpointing components like water and organic molecules in distant worlds, alluding to the possibility of habitable zones beyond our solar system. Following the development of the closest observed supernova SN1 1987A, it shed light on the life cycle of massive stars. These achievements cemented the Hubble Space Telescope's legacy as a foundation of modern cosmology, dazzling the world with its incredible discoveries. Its replacement, the James Webb Space Telescope, was launched to expand on the technological advancements and lessons learned from a model of our understanding of the universe's origins. This theory, today explained by the prevailing Big Bang hypothesis, states that around 13.8 billion years ago the universe started as a seriously hot and dense singularity, quickly expanding and giving rise to matter, energy, and fundamental forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the various structures observed today. The Big Bang theory also explains cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Despite being widely accepted, the Big Bang theory faced skepticism and challenges. In its early days, alternative models, like the steady-state theory, propose the universe without a specific beginning, and concerns about proof supporting the initial singularity expansion and observed anomalies arose. Most of these objections were addressed over time, and a significant piece of evidence came with the detection of cosmic microwave background radiation in 1965, aligning with Big Bang prediction. Space missions like Cobb and WAP, alongside technological advancements, further supported the theory. Accurate measurements of cosmic microwave background radiation adjusted strikingly well with theoretical forecasts. Enter the James Webb Space Telescope, equipped with advanced infrared instruments that can look through cosmic dust. The JWST, working primarily in the infrared range, captures the oldest light in the universe and observes objects formed shortly after the Big Bang. Its infrared abilities allow it to concentrate on star-forming regions, celestial nurseries, and the formation of stars hidden from optical telescopes. Infrared light, with longer wavelengths compared to visible light, can penetrate interstellar dust, overcoming a limitation of the Hubble Space Telescope. The JWST can observe cooler objects emitting mainly an infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their emitted light waves get stretched, causing a shift toward longer wavelengths. Red shift. The JWST infrared capabilities can detect these redshifted signals, capturing light from the early universe and offering insights into its formation and evolution. Energetic events like black hole mergers or new star births primarily emit in the infrared range, further expanding the JWST investigative capabilities. The telescope can explore phenomena that would otherwise be hidden or invisible. The JWST supplements optical telescopes like Hubble by having enhanced sensitivity and the ability to detect infrared radiation. This ability allows it to peer further into space and dig deeper into astronomical history, revealing hidden wonders and providing a more comprehensive view of the universe's development. The JWST serves as our window into the earlier phases of cosmic evolution. Recently, it revealed something so astounding that it might prompt a reconsideration of the entire cosmological model of the universe. We've discovered enormous masses of galaxies at the very edge of the observable universe. These ancient galaxies existed just a few 100 million years after the Big Bang during the cosmic dawn. The puzzling part is that we're unsure about how such enormous structures formed so early in the universe's history. This discovery might lead us to reconsider our understanding of the formation and evolution of galaxies in the early universe. Studying early galaxies is crucial for unraveling the mysteries of cosmic origins. The JWST can gain insights into how galaxies, stars, and planetary systems arose and evolved over billions of years. These observations also contribute to broader questions about the fundamental nature of the universe, including its composition, structure, and the forces governing its evolution. While the Hubble Space Telescope was groundbreaking for its time, it had limitations in observing the early universe. Its main limitation was its inability to effectively penetrate cosmic dust and detect the infrared light emitted by ancient galaxies. Older telescopes relied on visible and ultraviolet light observations, making it challenging to explore the early universe where these wavelengths are absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope represents a significant leap forward in observing gas galaxies from the universe's early stages. Unlike its predecessors, the JWST can observe celestial objects that formed within a few 100 million years after the Big Bang. Using its infrared sensitivity and advanced imaging capabilities, the JWST has uncovered an abundance of ancient galaxies, offering remarkable clarity and detail in understanding the universe's evolutionary history. Preliminary results from JWST observations have stirred waves in established cosmological models. The detailed data challenges several aspects of prevailing theories, prompting cosmologists to reconsider fundamental principles governing how we understand cosmic evolution and structure. Discrepancies between observed compounds. These findings theoretical predictions, valuable insights into the potential debates within the scientific of community. JWST observations might support life revealed a larger number of galaxies to exploring the early universe than anticipated. JWST is existing models suggesting understanding of star formation and rapid evolution process. The birth of stars. Some observed regions where young stars are surrounded, developed by dense clouds of gas and dust. Conventional models optical telescopes cannot penetrate with the discovery its ability of to detect unfathomable mass of galaxies. JWST captures the faintest distribution and arrangement these new stars of as they emerge from the revealing darkness, offering intricate and denser cosmic the processes that lead previously to star thought these planetary system formation raise fascinating questions. Studying these regions, astronomers for further exploration, gaining a deeper understanding of how structures challenges like early our sun come into existence. Cosmic structure formation over time. Another researchers to refine models for the JWST explanation is understanding how ability to peer into the structures gathered rapidly. Galaxies, black after holes, the Big Bang presents a puzzle. Massive that ones requires are believed to reside that the centers violate most fundamental principles of JWST. Significant disparities allow the conditions to observe the behavior of compared to predictions black based on providing new insight have also into their been revealed. Their these differences on galactic evolution, previously and the unknown physical energy they Unexpected conditions are unidentified. Astronomers piece together the story in simple terms these how galaxies variations and their central have prompted scientists holes to evolve together and improve our models. Others' growth. Moreover, the JWST is say discoveries that further exploration is required. Long-standing questions, but also raising observations as into a more comprehensive understanding of the universe, uncovering observations phenomena that often provide exciting theories into the universe. These challenges in-depth drive the scientific community to refine differences, cosmological models, and open observations may show specific research that properties or previously unimaginable. The discoveries galaxies that of the JWST are not just pushing reveal fluctuations of what we know composition structure, helping to reshape the fundamental pathways in principles of how we view the universe. Phenomena are incredibly complex and require careful investigation for us to accurately understand their true nature. Spectroscopy, a method that helps unravel the properties and history of celestial objects, is an example. It involves analyzing the light emitted or absorbed by astronomical objects by examining the properties of the light. Spectroscopy provides detailed information about the chemical composition, temperature, density, and movement of celestial bodies. This analysis helps us understand the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations differed from later investigations. For instance, initial observations of distant galaxies suggested a simple structure primarily dominated by lighter elements like hydrogen and helium, in line with theoretical expectations. However, spectroscopic analysis using the JWST showed fascinating variations in elemental signatures, identifying heavier elements or compounds previously undetected or misunderstood in the early universe. This challenges conventional ideas about the early universe's chemical composition and the mechanisms responsible for their development and DSP across vast distances. Similar initial assumptions about galaxies in the early universe were based on preliminary observations suggesting a relatively uniform pattern of development and organization. However, more detailed investigations by the JWST revealed a much more diverse and complex array of chemical compositions within these galaxies. The James Webb Space Telescope continues to redefine our understanding of the cosmos by shedding light on previously hidden corners of the universe. One of its most exciting capabilities is its ability to study exoplanets in unprecedented detail by analyzing the atmospheres of planets orbiting distant stars. The JWST can detect crucial chemical signatures such as the presence of water vapor, carbon dioxide, methane, and other organic compounds. These findings provide valuable insights into the potential habitability of exoplanets and the conditions that might support life beyond Earth. In addition to exploring distant worlds, the JWST is transforming our understanding of star formation. It can observe the birth of stars in regions where young stars are surrounded by dense clouds of gas and dust which optical telescopes cannot penetrate. With its ability to detect infrared light, the JWST captures the faintest glimmers of these new stars as they emerge from the darkness, offering a clearer picture of the processes that lead to star and planetary system formation. By studying these regions, astronomers are gaining a deeper understanding of how stars like our Sun come into existence and evolve over time. Another remarkable aspect of the JWST research is its ability to peer into the hearts of galaxies. Black holes, particularly super-massive ones, are believed to reside at the centers of most large galaxies. The JWST advanced instruments allow scientists to observe the behavior of matter around these black holes, providing new insight into their growth, their influence on galactic evolution, and the powerful jets of energy they emit. These findings are helping astronomers piece together the story of how galaxies and their central black holes evolve together, influencing each other's growth. Moreover, the JWST discoveries are not only answering long-standing questions but also raising new ones as it probes deeper into the history of the universe. It is uncovering phenomena that challenge existing theories and models. These challenges drive the scientific community to refine current cosmological models and open up new avenues for research that were previously unimaginable. The discoveries of the JWST are not just pushing the boundaries of what we know, they are helping to reshape the fundamental principles of how we view the universe itself.